fall, so.
I'm so sad.
Yeah. All right. All right, let's get started, guys. All right, so introductory things. If you guys don't know me, I'm Ismael. This is for College Physics 1. Hopefully you're in the right place. Before I start into it, I wrote these things because I know Caldwell lets you guys write your own formula sheets, and if you're not in Caldwell, I still think that these things are very important and they usually go undermined, so just take special note of them and understand their workings. So, especially with how much you've been practicing, I'm sure that kinematics, tension, stuff like that are very redundant at this point, but don't forget about them, remember, because each detail can cost you a point in the end of the day. So just to get a consensus of the idea, so we have two plans of attack here. One is that we go for straight 2 hours, I get through as much of the content material and then done. Or we can stop 30 minutes ahead, and if you guys have questions, I can ask those. But if you don't have questions, then we should do the 2 hours. So what are you guys feeling? Does anyone actually have any questions they have that they want answered? All right, so I think I'm just gonna go straight through and try to get as much as I can out. Again, guys, just so you guys know, 2 hours is not nearly enough time to cover all of Physics 1. I'm gonna try to do a general sweep through of all the material so you guys know what to focus on your independent study. But please don't use this and be like, oh, I'm good for the final. You still need to do some work on your own, okay? All right, so let's get started. All right. And if I ever start writing off the doc cam, please someone tell me, because I'm not going to be looking at it very often until the end. So if you can't see what I'm writing, let me know. All right, so the first thing we need to go over is vectors. All right, what are vectors, how to add them, how to play with them, and they're the basis of physics. Without vectors, you can't really do much because everything in physics is literally just a vector. All right. So if we recall, vectors require two components, magnitude and direction. All right. And in physics, direction is often dictated just by the sign of the number. Is it positive or is it negative? Will tell you the direction, while the number itself acts as the magnitude. Again, if you see on a graph, the actual degree or theta of the vector is its direction. So sometimes you might be asked, solve for the direction. It's just another fancy way of saying, give me the angle. Tell me what direction, what is the angle we were looking at, okay? Just a vocab review, if you remember, if you only have magnitude, it's a scalar. And it's really important to understand that we have our differences between vectors and scalars, because there are units in physics where you're going to be caught up and you're going to think, do I need the negative or do I need the positive? Does it matter? If it's a scalar, direction doesn't matter. It doesn't have a direction. You're pretty safe just going with the magnitude by itself. And these are things like speed, distance. It doesn't matter the direction you're traveling in. But other units, such as displacement, velocity, acceleration, these things are vectors, and we need to keep that in mind, right? Okay, so the next thing you guys need to know about vectors is how to add them. So there's two main ways to add vectors, and they're listed as head to tail and tail, tail, all right? Head to tail will just break out into simple addition or simple subtraction, depending on the direction. If they're going against each other, it's subtraction. If they're going to same way, it's addition. It's straightforward. 3 plus 5, it's 8. That's what the combined vector would be there. Now, tail to tail is most often when you have this type of situation. And if you remember, that's when you have to break out Pythagorean theorem to solve for the hypotenuse. Okay, right? Those are the only two ways to add vectors. So what physics loves to do is they love to give you situations where you're given 2 vectors or 3 vectors and they're not set up like this. So your job is to set it up in either head to tail or tail to tail, and we do that using trig to divide vectors into components. Just like this vector is made up from a and b, all vectors are made up of an a and b, or an x and a y to be more specific. So for example, let's get into our first practice problem. Okay, so you are tasked okay. Is that clear for everyone? You can tell that's 10 degrees and 30 degrees, right? And we're tasked to see, we need to add these 2 vectors, and we need to find the resulting vector. They're not at head to head, or excuse me, head to tail or tail to tail, so we can't simply just add their magnitudes. It won't work that way. So we need to get them into a position where they will be in our classic head to tail or tail to tail. And we do that by using trig to break up the components into x and y. And once a vector is in its x and y, we add up the x's, we add up the y's, and then we just do Pythagorean. So that would look like this, where we take this. So if we want the y value of this vector right here, you would need to do opposite over hypotenuse, because the angle is on the opposite side from the y, which breaks down to sine. So we're going to do 15 sine 10 degrees. And that will give us the y value. I'm going to label this a and this b just to be clear. And so that will give us the y component of the a vector. So we do 15, do 10 sine times 15. I got 2.6. Anybody else calculate that? Okay, we're good. And so likewise, if you remember SOHCAHTOA, the other one would just be cosine at that point. So we follow the same function. We do 15 cosine 10 degrees. Calculate what that is. I got 14.8. Right? And so now we have the x and the y component of our a vector, but now we have to associate the direction to make sure when we add it with the other vector b that it will add in the right direction. So we see that the y component here is going down. So innately we're going to label that negative. So this is a negative 2.6. While the cosine, the x-axis, is going to the right, we will label that positive 14.8. Okay? So now we know this is for vector A. This is the y, and this is the x. Now we do the same thing for vector B, which breaks down to the same exact math, where we just use the numbers for that one. So we're going to use 10 sine 30 degrees for the y, and then 10 cosine 30 degrees for the x. Get 7.5 here. Oh wait, no, I think that's cosine. Excuse me. and then 8.6 here. Everybody got that? We're good? Okay. And so now that we have the y's and the x's of both, if we were to take that and redraw it, now our vectors look like this. Also, before I move on, just know that this y is going up. What's up on? Let me just plug it in again. I might have put it in the calculator. 30 sine. Yeah, it's 5. I don't know why it gave me 7.5. Because I thought that, because sine 30 is 0.5, right? Yeah, that doesn't make sense. Good catch, guys. Is the cosine okay, or do I need to redo that? All right. So now that we have that, and again, those are both positive because it goes to the right and up. Does that make sense? So now we can associate that and redraw these vectors. We can now redraw them in their isolated x and y's. And now it looks like this, where I'll put it up in just 2 seconds, where we have a y component on the A, or the B of 5, a y component of negative 2.6, an x component of 14.8, and another x component of 8.6. Okay, right? And so now we see that when they're isolated, we see that the y's are going against each other. It's 5 minus 2.6, while the x's are working together, 14.8 plus the 8.6, because it's in the same direction. So when we add those up together, we now have a right triangle with an x component of 23.4 and a y of 2.4. Right? That's what we've broken it down to. And now we have the way, one of the original ways to add them up. We have it tail to tail. We can now just add them using Pythagorean's theorem. So now we can just do 2.4 squared plus 23.4 squared will give us c squared. And so c will be equal to I got 23.5. Okay. Is that it? For which one? This for here? Because when you add 14.8 and 8.6, because they're together, it's combined. So now if you're asked for the vector, would that be the correct answer? No, right? That's a scalar. We still need the direction. So now that we have all sides of our triangle here, we can now use any of the inverse trig functions to solve for the angle. Since you have all three sides of the triangle, it really doesn't matter which one you use, sine, cosine, tangent, as long as you put in the right sides. I like to use tangent, so that's what I want to show, right? So we're going to use, inverse tangent, which is the opposite over the adjacent. And in this case, the opposite, because the angle would be here, the opposite would be this, which is just equal to the 2.4, because they're both the same. So opposite, which is 2.4 over the adjacent, which is the side touching the angle, 23.4, and that will give you theta, which is equal to I got 5.9 degrees. Which makes sense if you think about it, because the x component was much bigger than the y component. So the angle should be closer to the x-axis. Okay, so before we move on, one thing to notate is, especially when you look at the entire course together, there are times where you need to use radians in your calculator, and there are times where you need to use degrees. This is where you use degrees. Radian, you only deal with it when you're doing circular motion. If you're doing straight lines, you're using degrees. Please use degrees, okay? All right, so let's move on. Also, guys, I forgot to tell you, but if you miss any of these notes or you want to review any of the problems or any of the things we did, this is currently being live streamed on YouTube, so it will be recorded. So if you ever want to come back, if you go to YouTube, put in Study Union 2018 College Physics, the video will be up, so you can rewatch this. Okay? All right. So now that we've covered vectors, we can now move on and we can now start talking about kinematics. So this is the next step. Okay. All right. So we're going to start simple with one-dimensional kinematics. So again, kinematics are just dealing with the quantities of motion. How do things move? How do they speed up? How do they stop? How far do they go? What direction do they go in? So first, before we can start actually solving for these things, we need to know the definitions and what makes up these quantities that we're going to be looking at. So again, so usually we have displacement. Displacement is just simply how far away are you from the starting point? Oh, are you away in a positive direction or a negative direction? I like to think of this like a race, right? You start at a start line and you're at a finish, right? So if you take a snapshot of a runner running a race and you take the distance away from the start line they are, that is their displacement. It's positive if you're going away towards the finish line. But if you actually start going backwards at the start line, you're going further away from the finish line. Hence, you're negative on your displacement. Okay? So displacement is just simply put, think of it as how far away from the start. Okay? While distance, again, is a scalar, so it doesn't care about where the start is. It only cares about how much did you travel. Regardless of how far away from the start point, if you're 1 meter away from the start point, you could have a distance traveled of, I don't know, like 1,000,000 miles if you went all the way around, you know? Doesn't matter the reference to the start point. It just cares about how much did you travel. Okay. So again, going on, we have velocity, also a vector, which is simply just put as the change in displacement over the change in time, which is how far away from the start point are you and how long did it take you to get there. And that will determine your velocity. All right? And then acceleration, following the same manner, is simply the change in velocity over the change in time. Are you speeding up or are you slowing down? How long did it take you to speed up to a certain point or slow down to a certain point? That's the question being asked there. It's really crucial that you have a firm understanding of these variables, because as you see when you're taking the test, they like to give you a lot of graphs that manipulate and switch up the variables, and you need to be able to re-put it together to understand the graphs. So as you can see, they're always a fraction of the previous variable. Acceleration involves velocity. Velocity involves displacement. So naturally, that will be reflected on the graph. So if we look at a displacement graph, right, and we say displacement is steadily increasing, then you know you're moving at a constant velocity. If for those of you who have taken calculus, just think of it as the derivative, right? You're just taking the slopes at each point of the graph and creating a new graph. And so the slope is the same at each point on this graph, so our points are just going to be equal. Thus, it follows so to say that, again, if we take that same derivative definition, the slope is rise over the run. If there's no rise, your slope is 0. So if your slope at every point along this graph is 0, then your point on every point of the acceleration graph will be 0. But if the math doesn't make sense to you, you can also logic it out. You can think, okay, I'm getting a certain displacement away from my start line at a constant rate, which must mean I'm traveling at the same speed. And if I'm traveling at the same speed, I'm not slowing down or speeding up, so acceleration has to be 0. It follows that line of logic. Okay? If that concept confuses you, I implore you, please practice more with those graph questions, because I promise you they will most likely be on your final. Again, take everything I say with a salt, because your professors could say, nah, I can do whatever I want. But that's a very key principle. So I'm going to move on now, because we just don't have time to keep practicing that. But at least that's a topic, you know. And so now that we know the actual units, we actually have to put them into an algebraic equation, which lets us solve for them whenever we deem fit. So again, starting with 1D kinematics, this is motions that happen on one plane of like motion. So it only happens on the x or only happens on the y. You don't have any angles. It's just going straight back and forward or up and down. They're very simple. So again, you guys don't have to memorize this. You guys in Caldwell, you can write it down on your equation sheet. For you guys and other professors, it will be given to you on the formula sheet or your kinematic formulas. But please understand how they work, right? So you simply have x. Okay, so those are all your formulas. And so essentially you have to know that they're linear algebraic formulas. So there's certain things you can do that will break these formulas that you really shouldn't do. And they will, and knowing those rules will also help you come to terms to what you need to assume when given a question and what you need to solve for. Because in physics, they never give you all the information in numbers. Sometimes they'll give you information through context, which tells you certain things about the variables. Number one, please don't ever put a position where your final velocity and your initial are both 0. It will not work. Your equation will break. Don't do that. So that tells you that either if you're going to assume the initial velocity is 0, that means you have to solve for the final. And if you're going to assume the final is 0, solve for the initial. You can't assume both are 0. It will not work. Okay? As far as that, typical trends, usually with 1D, if you're starting from rest or if you're not starting at rest, that will tell you whether you assume initial is 0 or final. Starting at rest, your initial is 0. If it doesn't say anything about starting at rest or it gives you an initial velocity, then you can assume that your final velocity usually will end at 0, especially if it's a free fall or a projectile, things like that. So what are like tips and strategies I can give you before we go into the practice problem? Two main things. Write what you know. And draw a picture. Usually you draw the picture first, but because these things will help you see through all the how can I put it, the trash that your professor is going to throw at you that doesn't really matter in context of the problem. It will let you see what's important and focus on the variables you need to solve the problem. So I usually recommend drawing a chart or a T-chart depending on the type of projectile motion and listing all your variables and going step by step and filling what you know for each variable and circling what you need to solve for. So let's see that at work with their practice problem, right? I have the practice problem on my phone, so 1 second. Okay, so we have a jetliner traveling northward, so jet traveling north. And it's with a speed of 69 meters per second. It has 750 meters of runway. In which it needs to reduce its speed to 6.1 meters per second. Yeah. Okay, so we need to compute the average acceleration needed to solve for this. What the heck? So that's what we need. This, and this are all essential things that could be important, but we don't know yet, right? So then we're going to draw a picture. We have the plane. It's traveling at 69 meters per second. This is our initial state. Our final state, we want it traveling 6.1 meters per second. And we have 750 meters. Our runway. Okay, right? So now we write. So this makes it really clear to see that our initial is 69, our final is 6.1, our acceleration is what we're trying to solve for, and our displacement is 750. Now the key rule with variables, 3 and done. If you have 3 variables, you now have enough information to solve for any quantity needed within kinematics. So that's the key you're looking for. You're looking to fill in 3 of the variables, because then you have time that's left. So that's all the variables needed. We have 3, so we can solve for acceleration and time. So now, using our formulas, we just plug and chug. And so we know what we have and what we need to solve for. So we're going to choose the formula that gives us what we need, as well as leaves out what we don't have. So this looks like a pretty good formula until you get to the end and you see you need time. So we're going to scratch that out. This one is the same thing. It needs time, so we don't use that. And that leaves us with this. We have final, we have initial, we have the displacement, so we can solve for A. So rearranging this formula to solve for A, it should just look like that. And so when you plug and chug your numbers, you should be coming out with 69, 9. An average acceleration of 3.15. Now, is it positive or negative? Yeah, because it's going in the opposite direction of your velocity. That's always the key term you want to go for. What direction is acceleration compared to velocity? If it's in the same, it's going to be positive. If it's opposite, it will be negative. Right? And so that is 1D kinematics. Any questions about that? Going once, twice, 3 times, sold. So it's not too complex if you just take it one step at a time and know the formulas, right? So moving on. Now we get a little trickier with two-dimension kinematics. Okay, so 2 dimensions, is like what the name says. It's now in 2 dimensions. We have both an x and a y we need to consider. But there are certain rules that we can apply onto the projectile, or in this case, like that's the type of motion 2 dimensions often falls under, that we can kind of limit the work needed to be done. No way. And so 3.15 negative is the acceleration. No problem. Okay, so a few things needed to know with 2-dimensional kinematics. The x and y axes, or axes, whatever, are independent. Meaning that they don't interact with each other. You can treat them as 2 separate one-directional motions, meaning you cannot substitute and replace variables. You can't say, if this final velocity on y is this, it must be the same for x. It does not work that way. Do not do that. They are simply just 2 problems merged together in one. Just treat it like 2 separate one-directional problems. Because if you start merging and things like that, you're going to get really confusing numbers that don't make sense. So that said, I'm going to contradict myself in saying there's only one variable that can break that rule, and that's time. Because when you think about it logically, if I throw this marker, they both, even the horizontal motion and the vertical motion of this marker will both end at the same time when it hits the floor. So time is transient. It occurs on both axes. That's the one thing you can assume will always be the same on both axes. It's time. Okay? So okay, and so now I'm going to star these because these rules only occur with a special type of 2D motion, which is usually the majority, like the meat and potatoes of what Physics 1 will ask you for when it talks about 2D motion, but still make a special note of it, and this is free fall. This is when you throw something, or pretty much what I'm trying to say, there is no acceleration on the x-axis, and usually the only thing affecting the y-axis is gravity. This is when these rules will work, right? So during free fall, you have 1, like I said, x-axis acceleration is equal to 0. Hence, on the x-axis, there's only 3 main variables you need to concern yourself with. That is x, v, t, and you won't have to deal with any other variables. So the x-axis during free fall will often just break out into any derivation of this formula or any different form. So x equals vt, x divided by v equals t, and you can just play with it. It's very simple algebra. That's all you have to do on the x-axis because there's no acceleration, right? Next is that free fall motion is defined by a parabola. Which looks like this if you were to draw it on a graph. Which makes sense. It's kind of what you imagine when you look at when you imagine throwing something. But there's certain geometric identities that we can pull from parabolas, such as when you bisect them in half, both halves are equal in all aspects, meaning the time it takes to get to the top is also the time it will take to get to the bottom, and so on. Also, so using that, you can often calculate for time. What's up?
What if you started at a different height than when you ended?
Okay, yeah, I'll cover that in just 2 seconds, because that is a special case that they will ask you, okay? And so, yeah, the main thing is to pull from that is time is equal on both halves. So often when you plug in your kinematic formulas, like I told you, you can't assume both the initial and the final velocity are 0. So how the formulas will play is that when you're solving for the y-axis and you assume that final velocity is 0, you're solving for this point. So don't forget to double time when you're going to pull time over onto the x-axis to solve for whatever you need there. All right. And like he asked, there's sometimes they're going to give you a situation where, let's say this is actually a cliff and the motion keeps falling, right? The rules about the parabola still stay the same, but you have to understand that they will only reflect the parabolic motion. So the time it takes to get to the top reflects the time it takes to get back to the original height. So often what you do is you break the problem in half and you try to solve the parabola first, and then you treat this section like its own one-dimensional problem where you just solve for the time and the velocity independently of the parabolic motion, and then you add them back together. Okay? All right. Does that make sense, guys? Is that following? You guys are really quiet. I know it's like finals, but push through. You guys got this. All right, so let's see a few examples of two-dimensionals, right? So I tried to do 2 examples. Again, the examples I'm pulling from might not have the same numbers, but if you go to UCF Study Union WordPress, there's a PowerPoint that has all the explanations that I'm talking about, all the problems that you guys can print and pull up and practice for yourselves. I'm going to try to change the numbers just a bit, but they're the same exact problem. So try to take this opportunity as see how I do it, and then go home and practice it for yourself, okay? So again, this is just a simple, okay, that's a poorly drawn football, please excuse me, right? And it's kicked off with 15 meters per second. And essentially, you want to solve for, this is a 30-degree angle. You want to solve for how far will it fly? This is poorly drawn. What's the height? And then also give me the time, right? So we're asking for a lot. But you can oh, yeah, sorry. Thank you. All right. Sorry for the poorly drawn parabola. But you can pull a lot of information from this. Just do you know how to, right? So first off, just like we worked with vectors, if it has an angle, we can break it up into an x and y component, which is crucial because, like I said, the actual axes are independent. And so we need to split the velocity into its x and y so we can see how they react independently. So we're just going to do what we did with kinematics and break it up, where 15 sine 30 will give us the initial velocity on the y, and then 15 cosine 30 will give us the initial velocity on the x. Right? So this saying, we just calculate those out to be should be 7.5 for the sine, and then about approximately 13 for the x. And so now we have our picture. Now we just draw out our axes and start labeling what we have. Right? So we know that the initial here is 13 meters per second, while the initial on this one is 7.5. We can assume the final velocity to be what? Yeah, 0, right? Because once it reaches the top of the motion, it will stop and it will start falling back down, right? Right? And so we can say that this will be 0. Our acceleration is what? Exactly, 9.8. right? Because it's falling, so gravity is pulling it. So we're going to put that as negative 9.8. We have our three variables. We can now solve for time, and we can solve for displacement, or in this case, h. Right? So now you just treat this like one dimension, and you just plug and chug your formulas, right? And so we have okay, so we can use, essentially we can use this one to solve for time and this one to solve for displacement. So if we isolate that, we get v final minus v initial divided by acceleration equals time, which is just simply going to be 7.5 divided by the 9.8, and that will give you time. You get 0.77 seconds. And if you do the other one, you would get v final squared minus v initial squared divided by 2a gives you the displacement, or in this case the height, because we're dealing with the y-axis.
Are the two kinematics negative or negative?
Wait, where?
When you're listing the three kinematical equations, you have VF squared is negative, I think.
Oh, that's not negative. This is me just marking which formulas we were going to use.
Okay.
Yeah, sorry. Yeah, sorry if that's confusing. Let me turn those into arrows. Okay, so those are the ones we're using. And so we plug that in, we get 7.5 squared minus 0 divided by 20, because I'm just rounding up. Acceleration is 9.8 to 10. 10 times 2 is 20. And we get a height of 2.8 meters, right? So now we've solved for the height, we've solved for the time. But now we can start converting back over on our x-axis. And remember that I said time is transient. So we can just pull time over onto the x-axis. But there's one thing you need to be careful about, is that this time we solved for here is the time it takes to get to the top of the motion, not the bottom. And because we know it's a parabola, we can just double it. So 0.77 should be around 1.4, right? That's the total time if you just double it. So 0.77 times 2, you get 1.54 is your time. And then we can solve for our displacement using our velocity times time, because there's no acceleration, so it maintains that velocity for the entire motion. And so we learned that our horizontal displacement is 20 meters. Any questions on that?
You use the first equation
For which one?
to find the x.
We use, let me pull up the notes here. On the x-axis, remember that acceleration is equal to 0. So you use these formulas.
Okay.
And so we had velocity, we had time. You just multiply them to get the x. Okay. Okay. So now you've seen how the math works, right? And now let's talk a bit about the conceptual stuff and what you might be asked, or at least ideas. So knowing that free fall is a parabola, what are some things we can always say for certain? One, that your final velocity at the top is always 0 on the y-axis, while your velocity on the x is constant. So no matter what point you draw on this parabola, the x velocity will always remain the same. It's constant. Also, we can play certain tricks with the y velocity now. Now that we know parabolas are equal halves, we know that they're like mirror reflections. So the y, the magnitude of the y is always equal to its opposite point, except flipped, right? So here, this y is like that. And let's say that this y is equal to 3. So here at its opposite point, it's going to be down, and it's going to be equal to -3. Does that make sense? That's an important concept. So you might be given a table where it gives you vectors or magnitudes of the different velocities at the different points, and that's how you can determine what your velocity should look like on projectile motion. All right? Another thing to consider here is that we can also use this to kind of predict which type of directions will impact our motion the most, right? So if we have 3 graphs, right, and they all have the same magnitude, but they're all going at different angles, and I asked you to pick which one would have the furthest displacement on the x-axis, it would be the one that has a moderate balance between x and y, right? So usually you can dictate what kind of angles you should expect. So this one that kind of bisects the quadrant 1, this one would be the correct answer. It would be the furthest. And if you were asked to give an estimate of what angle should be on that vector, it's always going to be approximately 45 degrees. While this one here, this one, the important thing to know about this type of graph is that it spends the most amount of time in the air, right? It has the largest air time. But inversely, it travels the less amount of horizontal distance. And so if you're asked for a theta there, this one will be approximately 60 degrees or above. Noted, and that said, with this final graph, its approximated angle will be 30 degrees, and it will give you the furthest horizontal displacement, but the shortest air time. So those are the relationships between those graphs and how they work with projectiles. Okie dokie. Okay, any questions? What's up, Anna?
What did you say about the first one? You said the third one is furthest horizontal.
Yeah. So excuse me, not the furthest horizontal distance. It will have, yeah, it'll have, excuse me, reset. This graph has the highest horizontal velocity, not distance. The 45 degree has the farthest distance. Excuse me, it's Monday. In my head, I swear I said the right thing. But good catch, Arnold. Thank you. All right. So any other questions about that? All right. So moving on. That wraps it up for kinematics. Kinematics will always still be present within other things you might have to do. So just be aware that questions won't always just be isolated to kinematics. Physics is very interrelated. So this is kind of acts as your foundation. There's going to be a lot of questions where you're actually dealing with forces or energy, and then you're asked to solve for kinematics on top of that, okay? So moving on. Okay. We have forces. So okay, so forces, I feel like forces tricks up a lot of students when they're taking this class, and we just need to take a small step back and just realize these forces are not too difficult as long as we can conceptualize what's happening in the problem. Because forces is just substitution. It's just chug and plug, or plug and chug, yes. This is why it's really essential. Like, you might not take me seriously about drawing the picture in kinematics, but here, please do draw force diagrams. I cannot expect you guys to succeed without drawing these force diagrams, because they give you all the information you need to know and tells you which formulas to use in order to solve for it. So, right? So, okay, so first off, our basis of the force diagram. This dot represents your object, and then the forces that act upon that object. And that's very crucial. Understand that force diagrams are forces acting on your object, not the forces your object is applying on other way. It doesn't work that way. It's forces acting on your object. Okay? So there are essentially 3 to 4 main forces that you need to know mainstay, how to solve for them, what are their formulas, how are they defined. Everything else is just labeled an applied force, which will usually be given to you. So these are the ones you need to concern yourself. Ultimately, you have Fg, or Fw, as some professors might notate it, which is essentially just weight, or gravity, like the force of gravity, right? And this is simply just broken down into your mass times your gravity, g. And remember, because some forces act against them because they're vectors, so they might be negative. So F1 might be 15, but F2 might be negative 13. So just keep that in mind, right? The next force is usually opposing gravity, and this often tends to be normal force or tension force, right? Depending on the situation. Normal force is the force of a surface that applies and maintains a position, right? It's the reason why that laptop isn't bursting through the table right now, because the table is providing an equal and opposite force, so they rest, right? And one things to notate about normal force, and even tension to a degree, is that they are mirrors. They only reflect the amount of force applied to them. They can never exceed that force. Otherwise, you would have a situation where you place your laptop on the table and it bounce off, right? That doesn't make sense. So remember, normal force, and the same thing can be said about friction. They only inhibit. They don't go exceedingly past something. So that said, that leads us into friction, which can be in that direction, but it tends to always be in the direction opposite of the motion, right? So if you're moving to the right, friction will be to the left. And then, all right, and so those are our mainstay forces that you need to know. I'm going to write down their formulas in a second. But also understand that the force of gravity is special, as if it's on an inclined plane, it can be bisected into an x and y, where here's how I'll put it, is that the x-axis and the y-axis are really interchangeable depending on your interpretation of it. But I will always say this, it usually works best if you think of it this way. The component that is running parallel to your surface, you will use sine. And then the component that is perpendicular to your surface, so always just think parallel to the surface is sine, and that I label FGY for sine, and then FGX would be perpendicular to the surface, okay? So now that you guys have that, how do we actually solve for these different forces, and what are they equal to, right? Like I said, Fg or Fw is simply mg, so it's easiest if we work with its components. While Fgx, which is what I like to notate it, it can be notated in other ways too, so don't refer on just the x, is the force of gravity that runs perpendicular to the surface, which is simply mg cosine theta, right? Most often, that force that runs perpendicular to the surface is often usually associated with normal force, and it's what you're going to use to calculate friction when you multiply its formula. Then Fgy is what runs parallel to the surface, and that's mg sine theta. Now the force of friction is simply just the normal force times the coefficient of friction, right? I'm going to notate coefficient of friction because there are some things you guys need to learn about coefficient of friction that I'll talk about in just a second here. And then essentially Fn will be less than or equal to Fg depending on the surface. Right? Like I said, normal force is only a force that can match or be under the force of gravity. So if you have a horizontal surface like the tables you guys are writing on, all the weight is going directly on to the table, straight on. There is no angle to be concerned about. That is when Fn is equal to Fg. But now if I were to take the table and incline it by any angle, that's what Fn is now less than Fg because it now becomes a component of gravity. And that component is equal to the perpendicular component of gravity. So if Fn is less than Fg, you will solve for Fn using mg cosine theta. That is how they relate to each other. And then notating that, because Fn now plugs into friction, Fn is just multiplied by the coefficient of friction to notate your force of friction. Now you can see why this gets a little confusing because they're all so interrelated. So just try to piece together each relationship. What's up, D? Depending on the surface. I ran out of room. So whether the surface is horizontal or it has an angle. Right? Okay. So coefficient of friction. What is coefficient of friction, just for any conceptual questions that may be asked? Coefficient of friction is the ratio of how much force it takes to push an object versus how much force it takes to lift an object. So usually, since it's a ratio, what that means is if you have a coefficient of friction with a number greater than 1, that means it is harder to push the object than it is to lift it up. So it is force of push over force of lift, right? So pretty much this idea is, can you think of any object that's harder to push than it is to pick up? Silence is good because yes, it's very hard to find an object like that. That's why usually your coefficient of friction will be under 1. It'll be a fraction. Because most of times in nature, it's always easier to push or drag something than it is to just pick it up and lift it entirely, right? And so because of that idea, that's why. And if you're ever curious about what actually has a higher coefficient of friction than 1, it's usually animals that can climb on walls, like lizards, spiders. They have special digits that on a microscopic level hook into the surface, and that's why it's harder to push on the surface than it is to lift them up. So just fun fact. Moving on. All right. So now that you guys understand the forces and how they relate, let's put some numbers to them and see how it works. So usually, most likely, is that forces will often be used to test your understanding of how they interrelate and see if you can solve for an acceleration or if you can solve for a system at rest. So they like to tell you certain things that will give you background information, like, for example, a car is traveling at a constant speed of 30 meters per second. What can you tell me about the forces there? Yeah, they're all equal to 0. Yeah. Or not necessarily, like their net, right? The summation is equal to 0. Let's be a little more specific with that. Because you can still have forces be acting upon you. Like right now, all of us are having forces acting upon you guys. You guys are being pulled by gravity, but you're also being pushed up by the normal force on your chair, right? It's always ever present. The only reason you guys aren't accelerating up and down is because the chair is matching the force of gravity, right? And so that's just the way you kind of want to think about it. So usually, let's just put, okay, forces, right? So usually what we want to think about with forces is First thing, what is A? Whether you're being asked to solve for it or you're being asked to kind of consider it, what is the acceleration? Because that will tell you a lot about how the forces are related to each other. So for example, if I give you this problem where this box weighs 10 kilograms on a horizontal surface, and just for the sake of convenience, I'm going to say he's pushing it on a horizontal axis. There's no component, so don't worry, he's not pushing down on it. It's just straightforward, right? And I say that he's accelerating with 2 meters per second squared. What can that tell me about the relationship of how much this person is pushing and the friction? Which one's greater? Yeah, the person. And so now we know that. So now we can start, we draw our force diagram, and so we want to know how much force is this man applying onto this box, or a woman, if whatever, right? And so we can now draw our force diagram. So we know that there's a normal force, there's an FG, and they're equal because the box isn't accelerating on the y-axis, right? So we can write that Fn equal to Fg because it's horizontal. And then we have an applied force by the man by friction, right? And you're given that the coefficient is 0.2, right? We can now have all the information we can solve for how much force this guy is applying. So first, if we look back at our net force formula, right, we know that the net acceleration is just simply net force divided by mass is equal to A, right? So essentially what we can say is that the net force is going to be the applied force minus the force of friction divided by the mass is going to be equal to 2. So now we just have to solve for force of friction and applied force, and it'll work itself out. So what we can say here is that, what do we know about the force of friction? What's its formula? Exactly, mu times normal force. We know mu, or the coefficient of friction, is 0.2 times the normal force, which we just dictated up here, that normal force is equal to Fg. Fg is the mass times the acceleration of gravity. So it would be approximately 10 times 10, 100 newtons, right? Times 100 newtons. And so we get a force of friction that is equal to 20 newtons. And so now we can just plug and chug. We can say that Fa is what we're trying to solve for, minus 20 divided by 10, and we get 2. You solve for that, 20, you multiply the 10, you get 20. You add the subtracted 20, you get 40. The applied force is 40 newtons. See, it's not too bad. You just have to keep in mind how are the forces related and how can we get from one point to the other. Okay. That said, we're going to go on a 10-minute break because I'm legally mandated to give you guys that because you guys are humans. So you guys can go get a drink of water, use the restroom. We're meeting back at 3:45. Okay? And when we meet back, we're going to jump into two-dimensional forces, and hopefully we can start getting into energy and rotational dynamics. Okay? Also, if you guys are really dedicated and you have any questions you want to ask me during this break, like personally, just raise your hand and I'll come by. Okay? What? It's all good. guys are nerds, dude. Like, I'm talking about like the 60-degree, and you guys are like, oh yes, we know this.
So like I'm
Yeah, it's fine. That's all good, Shadi. You know, it's really fine. Yeah, I was calc.
I was talking to my teacher. He was so nice to me. Like, but he was telling me like he's like you're a hard worker. You'll get through it. I'm like, yes, but
That's
you're
its-
still gonna make the test hard. It doesn't change anything. But
That's
it's
just.
nice to
Oh
know.
my God! Look how bad it's raining.
But it's pretty.
Yeah.
Did you guys go through like a lot in the first?
Oh,
Because
when.
I printed out the packet online.
Yeah, pretty much. Literally, when you walked in, we just finished talking about here.
That's what I was thinking. Because as soon as I opened it, I was like,
Yeah.
okay.
Yeah, like you guys only missed like the first 10 minutes, so it was really not a big deal. Like I just finished doing like one vector problem, talking about like solving for it. I can give you guys the notes if you want to look at it for a bit. Yeah, let me just pull it up. Yeah. How you feeling, Chris?
Yeah, I mean, you've been doing this countless times in SARC.
Yeah, this is just kind of like a everything we've done in SARC is how it breaks down. It's nah, this is the last day. Like Friday was our last day, and then this is our last like wrap up, and we're done for the semester. After study union's over, SARC closes up. You can still use the lab for like a place to study if you want, but there's no tutors. We're all done. Yeah, the lab should still be open for you to go in and use the boards and stuff like that if you want to study. It should be open from 8 to 7 p.m. Like, yeah, I don't like studying in the library either. I usually study in the SARC lab. Hey, just out of curiosity, what's the breakup? Like Caldwell, Dubay, like, if you're in Caldwell, can I see hands? Dubay? Okay, so it's pretty split. All right. Chris, can you do me a favor? When it hits 420, can you let me know? Like, I know it's funny. 420, blaze it. Yeah, no. Can you just let me know? Because I have to do some like bureaucratic things before I let you guys go. No problem, man. Hey, can I ask you guys a question? So we're falling a little behind schedule, so I want to know your preference. Would you prefer if I do more practice problems or keep breaking down the concepts? Like which one? Okay, practice problems. Okay, so this later half, I'm going to try to burn through like the actual concepts and talking about it, and then we're just going to do practice problems. So, all right, good to know. What's left so far is as soon as we finish 2D forces, we have energy, rotational dynamics, centripetal force, I'm going to highlight some things that I didn't have enough time to get to, but that I still think are important before I let you guys go, so you guys know what to focus on. But I think as soon as we hit rotational dynamics, I think we're out of time. I might try to talk about the graphs in simple harmonic motion, but I think by the time we get to rotational, we're done. Yeah, why? I think so. You can ask him. He knows. They want to know if the camera's still on during the break.
Yeah, it is right now, yeah.
Yeah. I mean, you guys probably can't be heard because the mic is over here. So. I don't know. Yeah. Okay. All right, guys. We're going to get started now. I'm going to skip this up a bit. Okay. All right, so getting started. So this is a good example of a two-dimensional force problem that involves tension. So you know that the pulley is frictionless, weightless, so we don't really have to worry about that so much. And that coefficient of friction is equal to 0.2, as usual. The box on the incline is 15 kilograms. The box hanging by the pulley is 10 kilograms. And we just need to solve for acceleration, right? So first, we're going to start with drawing our force body diagrams. So this one is just simply, it's held up by the tension, and it's pulled down by force of gravity. While this force here, this box, held up by the force of tension. Plus, we need to consider force of friction because it does have a coefficient of friction. Yeah, like that, or yeah. Just know that I drew them as two separate dots just for clarity, but they're still acting on the same object, right? So we have force of tension, force of friction in that direction. Then I'm just going to kind of squibble this in. Force of gravity, right? And then we have the component acting against it. That's parallel, so that's FGY. And that one is perpendicular, so it would be FGX for cosine. And then again, we have FN, right? I know that looks like a mess and an agglomeration. I am sorry, but do you guys understand what I'm trying to say there? All right. So essentially, one thing we need to keep into consideration with tensions is that they're very reflective of the two systems. So they like interchange pieces. So the tension upholding this block here will be equal to the force dragging this block down, while the tension upholding this block up is equal to the force of gravity pulling this block down. Right? Does that make sense? Because they're connected. What's up, D?
So to the left of the 13 kilogram box is the force of tension and
Yeah, friction. Yeah, friction is in this way, so it's tension, and then you have that, right? So we can kind of start solving for things. So we want to know what is the net force, excuse my awful sigma there, net force of this box. So we know that net force is a summation of forces. So we know it is going to be the component of gravity pulling the box down, which we labeled FGX, the one that is, or FGY, excuse me. FGY is the force parallel to the surface. It is pulling the box down. Added, or again subtracted because they're doing in different directions. So remember, these forces are negative in consideration of direction. Added to the force of friction plus the force of tension, right? So that's our summation formula. That's what we know is this system considering the box of 15 kilograms. Huh? FGY is this force here, pulling it down. And oh, yeah, I forgot to notate that. Acceleration is specifically of box of 15 kilograms, right? So now we can start plugging and chugging. So we know FGY is dictated by the component of gravity parallel to the surface, which we know to be mg sine theta, right? While FGX, or in this case, Fn, right, because it's an angular one, is notated by mg cosine theta. And then we know force of friction is equal to Fn times mu. Fn in this case is mg cosine theta times the 0.2, which is the coefficient of friction. Nobody's told me that I was writing off the... Come on, guys. Right?
Why that's the normal force? So what of mu is just the normal force times 0.2. So whatever you get for that one times 0.2.
Yeah. Because again, normal force times mu is friction. So if normal force is equal to the x component on a angled plane, then you multiply that by mu, you're going to get force of friction. Right? And now we have force of tension. But force of tension doesn't have a formula. But we do know that because they're interrelated systems in the picture, we know that the tension on box 15 kilograms here, right, this tension here is equal to the gravity pulling the box 10 down. That's how we solve for tension. So what is this force pulling this block down? It's gravity, which we can solve for as 10 times the acceleration to gravity, which would be 100 newtons. What's up, Jasmina?
The way Colwell does it is that he makes the tensions equal.
Yeah.
And then just changes the sign of acceleration.
Yeah.
So
Yeah, that's if you...
essentially you're doing the same thing, but you're just...
Yeah, just I'm dictating why he would do that. Like I'm giving the reason, right? So if you're changing the acceleration, here, this gravity would be 100 newtons down. This tension would be 100 newtons up, technically, by component-wise. Plus, also, Colwell does that in a net acceleration, where you're looking for the acceleration of the entire system as a whole. We're not doing that in this question. In this question, we just want to know the acceleration of this box. Does that make sense? Yeah. Right? Because it's only... If we're talking about the entire thing, that's when we talk about uniform tension. And that's what Colwell is talking about. Yeah, okay. So the box, we're solving specifically for that box, right? So what we're trying to say is that this is the summation for this box, just this box, this one. It's not the entire system because we don't compute for this tension. We're only talking about this box and what it's doing, acceleration of box 15. And so we're only concerned with the forces acting on that box. And that box is uniformly dictated by the tension, which is created by the box pulling down because of its gravity. What's up? Force of gravity is just equal to mg. And 10 times 10. Yeah. Does it make sense? Yeah. Because it's parallel, right? Right. Here, this one is a component of gravity. What is pulling this box down? Gravity. But gravity goes straight down. So it's bisected by this plane of the actual surface. So to solve for how much of gravity is actually pulling down the box, you use the sine function that's parallel to the surface, sine. And then that's how you can calculate how much of gravity is actually pulling down that box instead of just putting gravity itself.
Yeah, I know sorry after this, but is that always going to be the case of sine?
If you use the definition of it being parallel to the surface, usually, yeah, it works out as sine. There are some cases that it doesn't always work out to sine. If you're looking at it from an inverse angle, like if you, instead of given this 20, you're given like the angle to the vertical here, like it would be 70 degrees in this case, then you would have to flip it.
You said you were solving for acceleration of the 15, but
Yeah.
since they're connected, don't they have the same acceleration?
I mean, that's interesting. Yeah, I guess so. Yeah, that would be true. Because the net yeah, no, that makes sense for sure. I guess this is, yeah.
I guess he just does a different approach.
It's the same approach. I've just always defined it differently. Like in my head, this makes sense to me, but now that you're saying it that way, yeah. I guess it's really just a matter of because it makes more sense when I'm dealing with just this one. But yeah, because they're connected, you would just change the sign on them because if one's accelerating down this one would accelerate up. So I guess, yeah, the magnitudes of the acceleration are the same, if that makes sense.
So the 100 newtons equals the tension of the 15 kilogram box?
Yeah. And then the mg sine theta equals the tension of the, yeah. So like Jasmina is saying, since it's a system that they're connected like that, they're inverse, like they're all related, right? So the force of one is the tension of the other, and the tension of the other is the force of the other. Does that make sense, guys? I know it's like a lot of back and forth, but up or down, like here? Yeah. The other way, like, yeah. Yeah, okay. So essentially this force of tension is just going to end up being 10 times 9.8, or in this case 10, so I'm just going to 98 newtons. And so now we have all the factors of our summation formula, right? And so you can just add them all up, and you can just say that FGY is mg sine theta, so mg sine theta would be 15 times 9.8, it's 147, 20 sine times 147 is 50.3. Actually, let's do this. This is 50.3. The force of friction would be mg cosine theta, 20 cosine times 147 goes 138. We multiply that by 0.2. You're given 27.6. You know that's new. So if we have, we have 98 newtons pulling, so we have, oh, sorry. So the tension is 98 newtons, the force is 27.6 newtons, and then this force is simply just 50.3. So you can okay. And so you should get like about 9.5 joules. So that said, with that speed, it just barely like makes it up there, you know? Or wait, yeah. Yeah, that's pretty much essentially. So 103 joules is the amount of energy lost. When you take that into consideration with the actual potential energy related left, so pretty much how this would work out is you do the math and then you're going to be given answer choices where it's like the ball makes it to the top. The ball easily makes it to the top. The ball barely makes it to the top. Things like that along the lines of tests, like how can you relate the energy left over to like the actual status. So that means if we lost 9 more joules of energy, we would just make it to the top. If we lost any more than 9 joules of energy, we wouldn't make it to the top. So like, what's up?
Would the work done by friction be negative, or?
Yeah, it's negative, right? Okay. That's why I have it as negative. Oop, there. Oh, okay. Yeah, my bad. Yeah, the work done by friction is negative, and so this 9 joules is not, this 9.5 joules is not energy at the top. It's how much energy is left over after going up and being worked on by friction, right? Does that make sense? Because to solve for the actual full out energy at the top without in consideration, you just do 15 times 5 times 9.8. That would give you the energy at the top. But we're looking at the difference, like how much energy was left over. Okay? Okie dokie. So that's working energy. It breaks, what's up?
Well, why did you round trap?
Just for easy math.
Okay, so it makes
Yeah, it'll make it different, like
okay.
by a little, but just for the sake of time, I do 9.810 so I can do it in my head, so I don't have to plug it into the calculator. Yeah. But on your test, don't do that. Like, unless it says you can do that, don't do that. Like, I do it for the sake of time, but that's all. Okay. So now we have impulse and momentum. So key things to know about momentum, impulse. Momentum is just mass times velocity. P equals mv. The change in momentum is equal to j, the impulse, or also j is also equal to force times delta t. Okay? Those are the formulas. So that said, if I give you something like this, a problem where you have a force by time graph, and I say that this is 3, this is, you just solve for the area of the triangle, which would just be the base times height times 1/2. So you have 3 times 3 times 1/2, which gives you 4.5. So this is the change in momentum. So if you do initial momentum plus change in momentum, you will have final momentum. That's how it works. Same thing with velocity, same thing with forces, kinematics. So initial plus change equals final. And so we can reflect that and we can say that if our initial is 50, we experienced a change of 5, our new momentum is now 55. And so we can say 55 is equal to the mass times the velocity. The mass is 5 times our new final velocity. And so 55 divided by 5 will give us our velocity. Which is 11 meters per second. So that's the change. So impulse is usually very conceptual. They like to give you graphs. They like to tell you how does this impact this. Also, quick conceptual question. If I tell you a fly hits the front hood of a truck and which one impacts a greater impulse, what's the correct answer? Yes, it's equal. Please know that. That's free points right there if they ask you. And they tend to like to ask something like that. Again, it might not be a truck and a fly. They usually like to ask, this really big thing hits this really small thing. And a lot of people say, oh, the really big thing has more momentum, so it in fact impacts it more, but no, they're equal. Okay? If something really big hits something really small, like a truck and a fly, they equally affect each other in impulse. They impart the same momentum onto each other. I mean,
It doesn't really serve well with the equal and opposite
yeah,
reaction.
yeah. Do you have a question?
Say it because the fly may be moving faster, but has a smaller mass.
Yeah. Also, yeah, you can also witness that. Yeah, and that's why there's cases where you have in football where a really big guy tackles like a really fast, like small running back, and the running back can still push back the big guy because he has enough velocity. And they like to ask you the questions about that. So let me pull up an example problem about momentum and things like as in there's 10 minutes left of the session, not any other ideas, guys. I don't know. Okay, so what we're trying to say is, okay, speak of the devil, when I was just talking about football, all right? So if we have right? He weighs 60 kilograms, but he's moving 15 meters per second. He weighs 200 kilograms, and he is moving 2 meters per second. And they collide. You want to solve for which direction, who wins the collision, whether running back or the linebacker wins. And we can define this by saying, comparing their momentums, right? So the initial momentum must be equal to the final momentum because conservation of momentum. So initially their momentum will be 400 because 200 times 2 is 400. And then we do 15 times 60 for the other guy is 900, right? But they're going in opposite directions, so we have to reflect that in our math, right? So we're going to have one of them be negative. So our total momentum initially is just going to be 500, right? But now that they're collided, they're in contact with each other and they're struggling, whatnot, playing football, doing football stuff. And we know that the faster guy wins because the sign of the total momentum is the same sign as his, right? The faster guy has the positive side, positive 900, while the slower guy has the negative sign, negative. And our final is positive. So we know he overtakes him. We're still moving to the left. So we illustrate that with when they're combined, they're moving to this direction with a final velocity, which we can solve for by saying we add their weights. So now 260 kilograms is their new weight, and we solve for their final velocity by equating that to their momentum, which is 500, because initial momentum is equal to final momentum. So 500 is equal to 260 times final velocity. You divide out, and you're going to get a final velocity. That doesn't make sense. 500 divided by 260 of 1.9 meters per second to the left, right? What's up? Yeah, move it up. Okay, so we have, oh my goodness. So we only have 7 minutes left. So let me write down what I think is still very important for you guys to focus on in your independent study that we didn't get to in this session. And while I'm doing that, can you guys please finish up your notes and then fill out the surveys that are in front of you? And then also if you have any questions that you want to ask me, just let me know and I will hit them. So again, these are all things important to have on your formula sheet, so please have these and know these. But things that we didn't cover that are still important is rotational dynamics. So things to know about this is know how to convert between linear and circular. Convert linear to angular. And know, which is usually dividing or multiplying by radius do fit, right? Also understand rotational kinetic energy, which is the energy present in an object when it has both a linear kinetic energy, but it's also spinning, so some of that energy is going towards that spin. So I now have both, right? And so that rotational kinetic energy is solved by the formula IW squared 1/2. I being the moment of inertia, depending on the shape of the object, you're going to plug different things in for that. And then finally, understand how torque relates to rotational kinetic energy, and the fact that torque is like the force, the angular force, right? Where force is equal to mass times acceleration, torque is equal to I, the moment of inertia, times angular acceleration. So understand that relationship and that principle, okay? So yeah. Any questions you guys have for me? No? Okay. Well, good luck on your finals, guys. You're going to do great. Just make sure to have those things on your formula sheet and cover those that I didn't get onto throughout this session. And again, I hope this session acted more as a kind of a checklist for you guys to know, okay, he did this problem and I don't quite get it, so let me focus on that more. So I wish you guys the best and everything. So I'm still here for like another 4 minutes. I'm going to be collecting the surveys, and if you guys have any questions or anything, feel free to ask, okay? All right. The number, there's a number right under it that you just put in.
Oh, okay.
Yeah. Okay. Yeah, so 31, you just put 31. Yeah. Thank you. Huh? Yeah, this is it. It's been good, D-Man. See you, Chris. Thank you. Yeah, there's a number right under it, 30. Yeah, sorry, it's not very clear. Yeah. Oh, yeah, that's fine. No, it's fine. I mean, huh? Is the subject? I mean, I try my best to make it entertaining, but especially when I only have 2 hours and I gotta like burn through everything, like it's not the most interesting. It's just me like blabbing on for 2 hours. Like that's why I like our normal sessions because it's much more interactive and things like that. But don't worry, and I don't stress it because it's on YouTube. So if you ever need anything, yeah, yeah.
Are you posting like, is it just the videos on YouTube or like this document?
Yeah, everything that you see here is being recorded, so you can see it.
And I have a question really fast. So
Yeah, what's up?
I should know this, but so we had a question on a test. It was like a tennis racket spin. So there's a velocity that's 15 pot. It's like it says it's 15 meters per second, and then it hits it, and it's 15 meters per second. Would
That.
that second one be negative?
Yes. It's,
Shoot, okay.
yeah, it's a
Now
change
I
in
know what
direction.
that is. Okay,
Yeah.
well, I didn't know. because,
Yeah.
Like, on our
It g-
homeworks, it shows like when they're negative. or
Yeah.
I was like, I didn't
No,
think it was
sadly.
negative.
Yeah, and that's like an impulse question. That's where it comes in. So your impulse would be like the change. So you go final to initial. So you'd be negative 15 minus 15. You can see it's negative 30 divided by the
I
time.
did both ways, but I just picked the 0 guys.
Good luck, Shawnee.
All right, thank you.
No problem. Thank you. Orgo's miserable. All right, thank you. See you, Jacob. Have a good one.